Hello and welcome to the Makeup Lab for Unit 9's lab, Chemical and Physical Equilibrium. Purpose: to investigate the effects that various changes or stresses have on dynamic, chemical, and physical equilibrium. Furthermore, to use Le Chatelier's principle to explain the shifts in equilibrium observed in this investigation with regards to concentration and temperature. Background: countless chemical and physical processes that occur around us every day are fit into the category of reversible processes. The balance attained between each half of a given process is called dynamic equilibrium. The equilibrium that is established in a reversible process can be altered when an outside stress is placed upon that equilibrium. In this lab, you will be investigating the effects of several stresses on chemical and physical equilibriums. You will be taking a small-scale approach to the lab using small quantities delivered in plastic droppers to minimize waste as well as the impact on the environment. Even the smallest amount of something can affect the delicate balance of its surroundings. The equilibrium equations are as follows. You have equilibrium A with three substances. Noting to the right of that equation, you have colors for two of those three substances, one of them colorless. In equilibrium B with sodium chloride, we have the equilibrium between solid sodium chloride and aqueous sodium chloride in a saturated solution. Noting that NaClAq is equal to Na plus and Cl-, both aqueous and separate from one another in solution. In equilibrium C, 2NO2 in equilibrium with N2O4. For that one, we're starting with that one. Here in this round flask, we have this mixture between NO2 and N2O4. The NO2 is what gives it its distinctive brown coloration. But it's not completely brown because you have the majority of the substance in there in the N2O4 form. We're going to subject this round bottom flask containing this NO2 N2O4 mixture to two separate temperature extremes. I have here a beaker of very cold water and over here a beaker of very hot water. First, immersing it into the cold water, room temperature closer to the temperature of the water in this beaker. And with the white paper background, you want to see if you can notice a change in the intensity of the brown color. It's going to be made much more obvious when we go from this beaker of cold water over to the beaker of hot water. So the thing you're looking for is a change in color, darker in one, lighter in the other, and making the determination as to which one results in the darker color and which one results in the lighter color. Moving back over to the cold water. And back again to hot. Perhaps, if necessary, going back in the video, making a note of the times right before I pull the round flask out of each of the two extremes and then going between each of those two times in the video for comparison. In the data table under demonstration, record the change in the intensity of the brownness, more or less, when it's in the cold and in the hot water. So that was for equilibrium C. Equilibrium B's equation we'll look at next. This one calls for a test tube with sodium chloride. So we have that here. And in this test tube of sodium chloride, we're going to add 12 molar hydrochloric acid, a few drops of it. I'm going to add the hydrochloric acid when the test tube is in the test tube rack. Drops going in, looking in the solution and the bottom of the test tube. taking a closer look, looks like we have an almost snowy effect. It looks like a white precipitate has formed upon the addition of the HCl. And looking at the NaCl in equilibrium with NaAQ plus ClAQ, you want to think about which one of those three the HCl contributes. And from that, being able to decipher the shift, left or right, that this equilibrium takes once that additional HCl is added. So that was equilibrium B. Equilibrium A has us take a look at several stresses applied to the equilibrium equation given first. This piece of equipment is called a spot plate or a well plate, designed to get drops of various chemicals added to them for reaction purposes. Right now I'm going to place the stock solution, 2 drops of stock solution, in 4 different wells. The one there I just did first, that will act as our color control. So we have a comparison of a after color for each of these 3 on the bottom to the color of the original stock solution, which is of course right here. To well number 1, we're going to add KSCN, and it's the SCN that's a part of the actual equilibrium, and of course the shift change will result from that. So this is the adding SCN minus. Noting that it looks like the color of that got much darker, almost looking black in the video. Here in real life, it looks like a deep blood red color, almost black. In well number 2, before adding the iron as the procedure describes, I'm going to add this substance here, which will make the change that iron gives a little bit more obvious. So this resulted in a shift as well, and we can see a yellowish color resulting from the addition of that substance, oxalic acid. And now adding the iron back to it, it looks yellowish right now. Now it has a definite orange color associated with it. So it was yellow, now it's orange. You want to think about yellow plus what equals orange. Finally, we have well number 3, where we're going to add Na2CO3, 1 drop there. It looks like, in comparison to the color control, we have a definite lightening of that particular color. It also looks like there's a precipitate in there. The identity of that precipitate given in your data table, FeOH3. So effectively, when FeOH3 forms, you have the removal of the Fe3+ from equilibrium A, and the equilibrium will shift as a result of that removal. Complete your data table and questions, and turn your lab in to your teacher on the designated date that your instructor described. Thank you. This concludes Unit 9's Makeup Lab, Chemical and Physical Equilibrium.